Yes, welcome back to my channel. Let us now discuss one more phenomena in the magnetic field, that is called the Faraday's law of electromagnetic induction. So in this we know that there is a solenoidal coil and a magnet is taken and is slowly inserted into the coil and is always made to move through the coil. So as long as the magnet is moving through the coil, we find that an EMF gets induced in the coil. So this is known as the Faraday's law of electromagnetic induction. Now we see that the magnetic flux which is linked to the coil is changing. So only then the EMF is induced. If the magnet is stationary, then EMF is not induced in the coil. That means the rate of change of flux linked to the coil is important. So here we get the Faraday's law in mathematical form as induced EMF, if I write it as small e, that is equal to minus d phi by dt, where phi is the flux linked to the solenoidal coil. So this is the Faraday's law in mathematical form. This is for one turn of the coil. Now the flux linked to the coil can be written in terms of the magnetic flux density vector B bar as phi is equal to the surface integral of B bar dot ds bar. That means I have considered one coil here, one segment of the coil, and there is a surface area which is related to this one loop of the coil, and a magnet is trying to enter into this. Then the flux linked to the coil through this surface, that is given by the surface integral of B bar dot ds bar. So this is how we can write the phi, and then we can write the EMF induced in the coil. So if in this one loop of the coil an EMF is induced, we can write this EMF as the line integral, the closed line integral of the electric field at that point into the line element vector. That is, I take the line element here dl bar and I take the dot product of the line element vector dl bar with the electric field vector. So that way I can write the EMF induced as the closed line integral, because it's one closed loop here. So it's closed line integral of E bar dot dl bar. So here in the Faraday's law equation, E is equal to minus d phi by dt, we are able to write phi in this integral form, and also we are able to write the EMF induced in this integral form. Therefore we can rewrite the Faraday's equation as like this. So the closed line integral, that is EMF, the closed line integral of E bar dot dl bar is the EMF part, is equal to minus dou phi by dou t, and phi is written here as the surface integral of B bar dot ds bar. So this equation is known as the Faraday's law in the integral form. Now let us apply the Stokes theorem for the closed line integral. So according to Stokes theorem, the closed line integral can be written as the surface integral of the curl of the vector. So here closed line integral of E bar dot dl bar is equal to the surface integral of the curl of the vector E bar dot ds bar. So this way we can rewrite the Faraday's law now. Therefore we can write the left hand side as the surface integral of the curl of the vector E bar dot ds bar is equal to the surface integral of, here the derivative of integral can be written as the integral of the derivative. So derivative is taken inside. So you can write as surface integral of minus dou B bar by dou t dot ds bar. So both sides we have now surface integral. Therefore the integrand can be equated here. So on this side we have the integrand curl of E bar. Here we have the integrand minus dou B bar by dou t. Therefore we can equate the two. Therefore it becomes curl of E bar is equal to minus dou B bar by dou t. So this is also the Faraday's law equation, but this equation is called as the equation in differential form or point form. That means it applies to each and every point in the magnetic field.